Thank you. Hello, everyone. My name is Orhan. I will be presenting zero-resource translation with my collaborators Bhaskaran and Yasser from IBM, and Fatosh and Kuyongyong as my advisors. First, EMNLP seems to be doing good, so I will just skip the slide. And I will give a very brief introduction and another view from our perspective what the EMNLP is doing. So given a source sequence, first an encoder generates a set of vectors, which we call annotation vectors, and the set of these annotations will be called annotation set. And then at each time step of the decoder, an attention module first gives the necessary information according to this time step of the decoder, and decoder will use that information as a context vector as it generates the output sequence. So it basically consists of three components. As you see in the red, it has an encoder. In the blue, you see the decoder, and in green, we see the attention function or attention module. And we will stick to this color coding all throughout the presentation. So let's get back to the Warren Weaver's memorandum about mission translation. He was stating that do not shout from tower to tower if you want to communicate. Just go down to the common space, which he called interlingua, and exchange your information in that common space. And I will use this analogy throughout my talk. So how does it land, the color coding, how does that land into the interlingua? So we can think of the red tower as an encoder of a language, the blue tower as the decoder of another language, and we can think of this alignment function, the attention module, as the behavior of a car, an individual car. It gets its passenger and it passes the right information to the right position on the decoder. So there was some recent work about multilinguality, which we exploit a lot in this work. So I will not go into the detail of first three approaches. I will talk. This work is an extension of the last one, and we will follow that approach. Not that I have a personal bias of being that guy, but because that approach was initially proposed to do some zero-shot translation. So this is a follow-up work from many-to-many translation. Let's look at that approach. It was stating a multi-sequence modeling, a multilingual model can be modeled by using a shared attention module. Why is that? Because think about you increase the number of blue boxes and red boxes. How are you going to scale up with the number of green boxes, the attention function? So they proposed using a single attention function to model the interlingua, the cloud in between all the languages and all the languages. So essentially, the attention function here, what does this architecture tell? So let's increase the number of encoders and decoders, but let's keep just one attention function. So it does tell us do not model the individual behavior of these cars, but just model how the highway works. So they've used a more complicated attention function, but basically think about this cloud as a more involved function, which consists of two subfunctions. And it looks at the encoder annotation set. Here. This is the encoder annotation set. An attention function just generates a distribution first over this function, which we call alignment distribution. And then we take the weighted average of the annotation set according to this alignment distribution. And then another function maps it back to a decoder, a space that is understandable by the decoder. So we can actually use the superscript here to represent any encoder, and superscript here to represent any decoder. So it basically says that you can use a single function to pass information or to control the information passing from any encoder to any decoder. So what does this function actually doing? So this is our view of what's happening after the transformations done by this alignment function, the shared attention function, and we're going to exploit the fact that this function is actually satisfying some manifold properties. So what's a manifold property? Practically, if you're in a flat manifold, nearby points will have semantically close meaning. So this, for example, the representation vector, context vector for coming from a language should lie in some manifold that is flat enough. That's flat enough. And note that this manifold is it's indexed by the time step. So at each time step it changes. So we were asking this question how we can do zero-shot translation or zero-resource translation, and we started training a multi-way model using 3 encoders, as you see here. We train a model using bilingual text only, from English to French and Spanish, and from French and Spanish into English. When English is used as the decoder, it's shared across all the target languages. And the same is true when you translate from English to the other languages. And we will use only single attention function to control the mapping between encoders and decoders. So we asked at the very beginning, we asked the question, can we just do zero-shot translation? So what is zero resource and zero-shot translation? Zero-shot translation, you don't train your model between 2 pairs of languages, and during test time you just ask the model to translate between those 2 pairs. Zero-resource translation is something you will not give an access to the source and target pair of this zero-resource pair. So your model will not see any examples that corresponds to those 2 languages. But during test time, you can actually generate some data and use that data inside of your model. And our initial experiments show that if you do zero-shot translation between Spanish and French, you were barely getting it was barely getting 1 blue score. And it was a bit disappointing, so we tried pivotal translation. First, let's go to Spanish to English, and then use that generated English sequence to translate into French. And that was looking good. Actually, it was promising. Here you see the translation score. 20.4 is the pivotal translation baseline, and we will use this blue score as our baseline. So what we can do in terms of zero-resource translation, so we were given, let's say, English-French by text. So we can generate some Spanish data using using the English side of our by text, and then using the target side of French, and then generated Spanish data. We can fine-tune this pair, this path, but only fine-tuning the alignment parameters. I mean the attention function. So what does it mean? So it means that you're updating the alignment for underlying alignment function, attention function here, to put the representation into the right spot. And then hopefully the decoder can understand depending on the point that the representation lies in this manifold. So let's look at the results that we got. So we generated some pseudo-parallel corpus beginning from 1K all the way up to 1 million byte text. We also replicated the experiments with true parallel corpus using the same amount of data. Here you see our baseline test score. It's pivotal translation. And when we generate 1 million pseudo-parallel corpus, we were achieving 70.6 blue score. So it was not doing that good, just by fine-tuning the alignment function, underlying alignment function by the pseudo-parallel data generated by the model itself. So we took a step back and asked ourselves the question, so what else can we use this model for? So we trained a model which has 3 encoders and 3 decoders. Can we actually do something else? So we found out that actually this model can be used in multiple decoding. It can be used to do multiple decoding during test time, decoding strategies during test time. So the original proposal of multi-source translation came this year from Zoff and Knight. So what they were doing is actually they were using multi-text, and they were training their model using this multi-text from Spanish, in their case Spanish and German, French and German into English. But that necessitates a merger operation, which is a parametric operation, and they were using a complicated architecture to do that. But our goal was to do it. During test time. So we will not be given access to any multi-text during training, but during test time we will have access to this multi-text. You can think of news test development or test sets as a multi-text because it's n-way parallel. So we came up with two strategies, actually three strategies, that we can exploit this multi-text only during test time. So we came up first with late averaging, which is basically a model ensemble. So you can actually do, you can translate from Spanish to English and French to English and then take their average, the average of the probabilities. Or you can actually do another thing, which we call early averaging, which is applied only during test time. And it will look at both representations, and we will do some tricks, not tricks, very common operations exploiting the manifold hypothesis. And then it also generates an output as if it was coming from one encoder. And we will first start with using the very basic operation, taking the mean of this context representation. So we were going to use the same attention module here. So one single alignment function is going to be used across all the source pairs. So at the first, for the first source, alignment function will look at the context annotation set and will give you a context vector, and we will replicate it replicate this process to the second source here, and we will end up with two context vectors coming from two sources. And then what can we do is we can just take the mean of these two representations. And if this space is a manifold, so the close by points should also lie in the manifold. And we saw some improvements, a huge improvement actually, when we just take the mean and feed it as to the decoder as it was coming from a single encoder. Single encoder. So let's look at the red curve here. This is the validation set negative log likelihood plot. The green curve and blue curve corresponds to the negative log likelihood on the validation set of single pair models, French English and Spanish English. And when we look at the red curve, that corresponds to just taking the mean during the test time of the multi-source. So we came up with three translation strategies that can be used during test time only. So early averaging is just taking the mean operation between these two context vectors, and late averaging corresponds to model average. That corresponds to model ensembling. We can also ensemble early and late average, which we call early plus late. So let's look at the blue scores when we do when we apply the decoding strategies during test time. So on the left, you see the baseline performance of this multilingual model, and highlighted on red, you can see single pair translation results. And okay, for Spanish English, we were getting 28.3, and for French English, we were getting 27.9. And when we use multi-source during test time, we were able to get almost 4 blue points improvement with early plus late averaging. I want to emphasize that the model has never seen any multi-source during training. So this is just applied. This technique just applies to test time. So what does it mean? We can actually exploit this test time fact because we are also trying to do zero resource translation. What we can do, we were using only information coming from the pseudo-parallel generated data. So it was corresponding to this point. So we were trying to pull the representation into the right spot here, but we were actually ignoring the other source. So we were actually generating some Spanish data using English. This Spanish generated data was used to pull the representation here, but then we were discarding English. Let's just use English during test time as we were doing multi-source translation, along with the pseudo-generated Spanish data. So our target will still be gold standard data, but one of the sources of this multi-source path will be coming from pseudo-generated data. The other one will be gold standard data. So what does it mean? We will not only use the information coming from noisy generated data. We will also use the fact that where should the mean of this two context vector lie in the manifold. So we are just introducing additional information to the model. So we end up with a teacher-student network. So in the first update, we were updating only the corresponding parameters of the attention function to update the zero resource pair here. As you see, it was the Spanish-French path. And in the second update, we were also using this multi-source information. You can think it like the multi-source path is actually pulling the information to the right point by giving it a guidance from the point where the mean should lie. And we alternate between these two steps by using the generated data, and we fine-tune our model, specifically alignment function, a little bit to achieve better performance compared to pivotal translation. So we can check the red underlined numbers here by using this teacher-student fine-tuning strategy. So we were able to achieve, by using 1 million pseudo-parallel corpus, we were getting 1 blue point better than the pivotal translation. And surprisingly, by using only 10,000 samples, pseudo-generated samples, we were able to beat the pivotal translation. And also by using true parallel corpus, we were also able to get good results when we use 1 million gold standard data. One interesting thing is, up until 1 million true parallel corpus, actually pseudo-parallel corpus performs better. So we thought that we were thinking that maybe the pseudo-parallel data is reflecting the inductive bias of the model better, and also it has a lot of noise, so it might be thought as a validation, as a regularization, because this amount of data is still quite low. So at the end, what we have learned from this, we don't necessarily need a direct resource between any pairs to do machine translation. If you train a multilingual model, you can actually generate any pair in this model by the model itself without training an additional corpus, training an additional model, and then you can use that generated data back in the model to fine-tune some specific parts. And multilingual machine translation naturally embeds multiple decoding strategies, as we saw in early averaging and late averaging. And we just needed to tweak the alignment parameters slightly. So we don't tune any other parameters, not even softmax, not even encoders or decoders. We're just tweaking updating the alignment at the attention function parameters, which was corresponding to this cloud. But we assume that we already have well-trained encoders and decoders. As in our case, all those encoders and decoders were trained using a large amount of bilingual data. And what are we thinking about the future work? One thing we didn't do is we can actually train the model in an online fashion. So what we did was we generated some data and used that data to fine-tune the model only once. But what we could have done something better. We could have generated some data, use it a couple of epochs, and then generate some more data and use that in an online setup, which would get us better blue scores on the zero resource pair. And we also only considered translation between 3 source languages and 3 target languages. If you want this alignment function, if you want this highway to generalize to the unseen parts, we should actually take the number of encoders and the decoders to the limit. Then it will be easier for the attention function to generalize to the unseen parts. And at the end, we still need more investigations on the zero resource path, because it's zero resource and it's not zero shot. And thank you all for your attention. You can find some starter code in the DL4MT habitat. I should also thank IBM, Samsung, Google, and Facebook, since this work was done while I was a research intern at IBM. Thank you all.
Hi there. Very interesting work. I was wondering, how close do you think your multilingual models are to representing the source sentences in a truly multilingual space. So it would be really quite interesting to maybe see, a sentence in English and a sentence in Spanish, and how similar their embeddings really are once you've trained this model in a multilingual setting.
So in this model, since we're using attention, we don't end up with a fixed length vector that's coming from one language and the other one is coming from other language, and we are using an attention. So we are using a set representation for each of these sentences. So you need to find out a way to measure the distance between two sets. That doesn't seem to be trivial, so that's why we share the attention function and explore the intrinsics of that function. That seemed to be easier, but that's a good research direction, I think.
Hi, this is Uday from Apple. Very nice work. I'm just curious if you also updated encoder and the decoder with this multilingual training. Would you have gotten better results? Did you try it?
We did not try it because of some time limitations.
Okay, thanks.
Thank you again.